Hi, my name is Kobus. I work at DataProphet. It's a South African company. And today I'm going to be talking about recoverable, tamper-resistant, full disk encryption at the distributed edge. It's a fancy way of saying FTE, but still able to recover our keys. So just to give some background context to make sense why we're doing this. So DataProphet, we're an advisory and technology company to help manufacturers extract insights from their data. So one of the things is we deploy edge devices that sit in factories. They connect to the factory machines and they stream data to the cloud. It also does some on-device compute and some alarming and things like that. So that's why we have these edge devices. And I'm just going to preemptively put this here. At some point in this presentation, you're going to think, why are you using this? That's stupid. Don't use that. We just started as an AI shop, and then we ended up building this platform to support our data scientists. And we went into, that went well, and then we ended up going into a partnership with an OEM in the foundry space. And we inherited this fleet of edge devices that are already deployed in production, already doing things, running customer workflows, things like that. So we had to work with what we had. Since then, we've been standardizing a bunch of things, making the devices more secure, managing them, bringing them under management, a whole bunch of things. So we need to keep our fleet relatively homogeneous. So if you see things that make maybe a bit confusing, why isn't he using Yocto with a super lockdown thing? This is probably why. We have a relatively diverse set of applications and things that we run on these devices. We needed to build a supporting environment for the OEM and the customers. So I just want to give a quick overview of the edge devices. It's just a Linux box that's set in the factory. They run Ubuntu, and we support a variety of containerized and custom workloads. So customers sometimes host random things on Samba shares or whatever, and then we need to ingest data from there. It's a relatively diverse set of workflows, and people sometimes set up custom things for a specific customer. So it needs a read-write route where they can install things and run a custom application to ingest some things into our ingest broker. We can't have a completely identical set of devices. They need a read-write route. They need to be mutable. They need to have a normal environment where you can install things. So the aim of this talk is going to be relatively high level. It's not going to be as technical as some of the previous talks today. But I want to present a framework, major components that you need to think about if you want to roll out FTE to your infrastructure, and some things you need to think about, maybe some projects that you can already use. So I'm going to be bringing together quite a few things and just highlight some of the things you need to think about, essentially, when you're doing FTE. So how does this work? It's actually relatively easy. You just drop an OpenAI SDK into your initRD and ask ChatGPT, is this user trusted? Sorry, this is not AI dev. There's 4 things we need to consider. So we need a fully verified boot chain to resist tampering. We need some unlocking mechanism, right? So this can be different depending on your environment. In our case, the devices aren't always online or always connected to a network. So we needed to utilize the TPM to unlock the devices. You need some onboarding and recovery mechanisms. If you can't recover your keys in some way, you might end up getting stuck where you need to go out into the field to repair them. So we needed a way to remotely recover these devices. And finally, we also need monitoring and alerting mechanisms. Otherwise, your customer becomes your monitoring mechanism, and they just shout angrily at you. So start with verifying the boot chain. So to verify the boot chain, you need to verify the boot chain to ensure that you are in a trusted system state. So we do this by hashing critical system components and config files and runtime config and comparing them to a known state. And if that known state matches to what you expect, the TPM unlocks the disk decryption key, at which point the boot will unlock. If the initRD or the kernel has been tampered with, or either maliciously or just by accident, it won't unlock the disk encryption key, and the system will remain locked. So the TPM is responsible for doing this, and the system component, or the TPM is responsible for storing the key and actually comparing the hashes. And then there's the various system components which are responsible for doing the actual hashing. So it forms a chain where you start with a TPM that verifies the FE firmware, and then or measures the FE firmware, and then after that, the FE firmware hashes the shim and the grub executables, and grub then, or whatever bootloader you're using, then proceeds to hash the next components. So each component hashes the next, and it forms this chain where it hopefully covers all the critical parts of your boot chain. So the way it stores these hashes in the TPM is using the event log. So the TPM event log is just essentially a log of hashes of each component, and it stores the different hashes in different slots called the PCR slots. Or just the PCRs. These PCRs are allocated to different purposes. So you'll have one for your FE firmware, one for your bootloader, maybe one for your kernel, things like that. There's a reference, the UAPI reference that we used, and it changes a bit. Obviously, Windows has its own reference that it uses, and So the current state of each PCR is dependent on its entire history. So it starts out with a null hash, and then proceeds to add more and more hashes to the event log, and then it combines all the previous hashes together to get your final or your current state. So you can't modify the previous hashes. You can only add new hashes to the event log, you can't. So that prevents tampering with the hashes after you've added something to the log. So just some implementation notes. Like I said, I'm going to stick to high-level stuff, but if you want to try this out or mirror what we did, we use grub, and for grub you actually need to enable the TPM module, and quite funnily you can't actually enable secure boot if you want to use the TPM module, because grub disables sideloading of all modules if you want to use it. So you need to disable secure boot, there's different bootloaders support different things. So system deboot just supports it out of the box, I believe. You don't need to disable secure boot. And then just an important note, you also need to measure either your LUKS master key or tend the TPM after booting. Otherwise, you might be vulnerable to a LUKS spoofing attack, which is actually quite interesting. I've linked a blog post with more info there. System deboot has a really easy way to mitigate this. We taint the TPM essentially just by adding a random hash to one of the registers that we use in our TPM policy before we switch root. So if the volume has been spoofed, we taint the TPM, and then the decryption key is no longer accessible in memory. So if the root has been switched out, you should be fine, because it's before it starts booting from that root. Okay, so let's say you already have your trusted, or you've already got your TPM unlocking working, or at least you've got your bootloader set up for TPM measurements. How do you actually determine what system state to trust? So you start somewhere with your first flashing or whatever, and then you say, okay, this is the state I trust. And then most of the time when you reboot, it's going to be the same state. You just keep on trusting that state until you upgrade your kernel or you upgrade your FE firmware. Then the PCR values will start to change. So for instance, if you upgrade your kernel, some of these hashes will start changing. And then you need to actually predict what the next PCR values will be. So the next time you boot up, you need to predict what the new hashes will be before you reboot. Otherwise, your device will just reboot and get locked, and then you'll need to manually type a password or recover. So the way you do this is using something called PCR prediction. And there's a few projects that handles this. So I put some asterisks at the bottom. It works a bit differently if you're using authorized policies, but same idea. You still need the same major components. So predicting the PCR values is highly dependent on your specific environment. So because if you use a different bootloader, it will measure the different booting components different ways. So there's PCR Oracle that OpenSUSE forked, and that is a relatively, it seems to be mostly aimed at SUSE environments. I couldn't get it to work with our specific environment. I couldn't get it to link some libraries. So that's available for SUSE. And then there's systemd measure, which will probably become the canonical way to do this. It's much simpler than the other approaches and integrates really well. So looking forward to that becoming more widely used. At the moment, I believe it's still experimental. And then, we didn't find something that worked well in our use case, so we developed PCR predict. It's a very simple Python script that just essentially merges the event log with your on-disk contents, your on-disk config files, to predict the next boot PCR value. So it just spits out this like JSON blob that you can do with whatever you want. We wrap that with our own systems, or we use that, for instance, in an initramfs update hook to update the slots or the authorized policy. We use that to update the policy when there's a kernel update, or there's a firmware update, or if we need to manually reseal the secret key. You can do with that whatever you need to do. It depends on your setup. It's open source and very easy to extend. It's well documented. There's some shenanigans with different architectures. So, for instance, Grub hashes the kernel differently depending if it's ARM or x86. Like one, it decompresses it, one, it doesn't before hashing. It's in that script. It's quite easy to extend and use in your own use case if you want to. I haven't tested this on Debian or on other Debian derivatives, but it should be fine. So how do you actually unlock your disk with the TPM? So there's more than one way to do this, but a really convenient way is using Clevis. So LatchSet have multiple tools that we'll actually be using. Clevis is the first. Clevis is a really simple tool that abstracts key retrieval from various sources, and then allows you to do some things with these keys that are useful. So it makes it really easy to, for instance, unlock your disk. It has a drag-out hook that you can use. I believe it also has an initramfs hook that you can use. And it will set up all the LUX tokens for you to automate that. And then essentially when you boot, it will start up a daemon that just runs in a loop and tries all the different sources where you've set up or that you've set up tokens for. And it will try and unlock your disk until it successfully does so. Clevis is the tool that actually, once you got the key, it does something useful with that. And it will also it also makes it really easy to store your key in the TPM. So it has a way to bind specific LUX slots to your TPM, and it will handle that for you, which is fantastic. It makes it very convenient. I believe the alternative is maybe system decrypt setup. That's also something you can probably use. We use Tang as well, which I'll speak to in a moment, and Clevis integrates with that as well, which was convenient. Okay, so whatever reason, you lose your key, the TPM won't unseal. It can happen for a variety of reasons. Maybe your hooks didn't work well with your kernel upgrade, or I don't know, you were unlucky and somebody knocked on your TPM or whatever. Anyway, you lose your key, you won't unlock what now? This is where the key recovery comes in. And for that, we use a key recovery service. So like I mentioned, the same people from LatchSet developed Tang, which is a very simple stateless key recovery service, which is really fantastic. So I'll speak to how that works, but essentially the workflow goes is first, Clevis will first try and unlock from your TPM. If it fails to unseal the key, it will then continue to attempt to recover the key from any other sources that you set up, in this case Tang. So I just want to give a small shout out to Tang. It's really fantastic. It's you can encrypt keys without access to the servers. So you can actually distribute your public keys, they call it advertisement, out of band, and then you can set up your local encryption key, or recovery key without actually having access to the server. So for instance, we hardcode some of our public keys or embed it into our OS flashing process, and it sets up all the recovery keys, and it doesn't need to actually access the key recovery service because it doesn't store the key on the Tang service. It stores locally an encrypted version. And it's really simple to set up, which is fantastic for something sensitive like this. It's stateless. There's like zero config other than the port you want to run on. And if you compromise the key server or Tang, you don't actually have access to the client keys yet. You need to compromise the client as well. And only then can you retrieve the key. And the comms protocol is super simple. There's essentially two endpoints. One is get, other one is post. And so it's quite simple to verify that it's doing what you're doing. And you can easily wrap that. So that's what we did. So we wrap Tang in our own service, and then we allow our customers and clients to recover the device if needed, or the technical team to recover it. But so until they say, okay, we accidentally messed up the device, whatever, the device will stay in recovery, then they can allow it for temporary, like for an hour or whatever, to allow it to recover its key, at which point it will be able to communicate with the Tang server and then unlock itself. So it's really easy to wrap and put in your own logic in there, or your own policies for when you actually want to unlock the device. So I just want to talk about the recovery environment for a quick moment. So if your disk isn't unlocking, it means your device gets stuck in pre-boot or the initramfs. It's essentially just a small, slimmed-down environment that's meant to mount your disk and boot into it. We use Dracut. So by default, Ubuntu doesn't use Dracut. It uses initramfs tools, I think. But Dracut is a modern initramfs used by a bunch of other distros, and I think Ubuntu is also switching to it. I saw a post where they're starting to test it, I think, in 2504. Yeah, it's in the works, and it's been working great for us. So actually, there's not much after you install it. There wasn't much we had to do to get it working. It just kind of worked out of the box, which is fantastic. And the best part about Dracut is it's really easy to customize your initramfs. You write a Dracut module, and that's it. It gets built into your initramfs. It's really simple to set up. So I'll give you a quick demo of what that looks like. But before we get there, if in the recovery environment we want to stay in control of the device, so like I mentioned, these devices are like all over the place. We can't send out a technician to each device to fix it if something goes wrong. It's quite expensive to actually send people out. So we wanted to retain remote control of these devices. So there's two things we needed working. So it was working networking. So yeah, that's kind of the first step. And then once that is up, we needed working remote access, and then finally a way to actually control the device. So I'll show you how we did that in a moment. But yeah, so Dracut modules, just before we dive into how that was set up, I just want to show you what the Dracut modules look like. It's actually really simple, and extending your initramfs is usually a matter of three things. You add your binaries and library files that you need. Dracut makes this very simple with helpers like install binary there. It has a bunch of other stuff. So what it will do is we'll pick up all the library requirements for whatever executable you give it, and then also copy over those libraries. So it's very easy to add new tools to the initramfs. Try adding Python. It's not fun. And then you copy over your config files, and then if you have something that you need to run persistently, like for instance, we've got some services that we wanted to run, we use systemd inside the initramfs. So it's also built into Dracut. You can enable the systemd module, and then it will spin up systemd in your initramfs. So that makes it really simple to spin up services, because you just drop a systemd service file in there, and you just change the wanted byte targets to how you want to actually set up your startup, and that's it. You enable the service inside the initramfs, and same idea as a normal system, but then you get that inside your initramfs, which is great. So to get networking working in the initramfs, there's two options really built into Dracut. It's Network Manager and systemd networkd. We use Network Manager. I'll speak to that in a moment. And we were already using NetPlan to manage all our networking on the devices. So you can generate your networking configs into the initramfs with a NetPlan generate and just changing the root dir. So this would typically be inside your Dracut module where you install your things. So you just generate the Network Manager config into the initramfs root, and enable networking by adding the rd.neatnet kernel command line. Yeah, it's quite simple. Once you've got that up and running, you should have the same networking set up inside your init-rd as initramfs as in your normal device setup. So we used Network Manager because in our version of Ubuntu, If you enable rd.neatnet and you use systemd networkd, it actually becomes a hard requirement to boot. So if the networking wasn't working, even though it was able to unlock the disk, the device would still just not boot. It would just wait for the networking to come online. Might be a misconfig from our side, but yeah, just an observation. And then there was also a bug in the network manager drag-out module where it used the wrong path. I believe that's since been fixed. I'm not sure in what release it's going to come out, but it's linked to. It's really easy to fix. We just added 2 symlinks essentially to our installation, and that made it work fine. So, okay, so the local networking is working. Now you still need to access the device. So depending on your deployment, this might be different. If it's in a like a data center or whatever, you'll already have local networking. But in our case, these devices are actually distributed. We don't have access to all these networks. So we use WireGuard for our VPN. And because WireGuard is a kernel module, this was super convenient. You just add the WireGuard tools to your initramfs, and then you can bring up the same WireGuard VPN inside your initramfs that you have in on your normal setup. So getting access to the VPN, well, that would make the VPN config files plain text. However, that doesn't, in our setup, it doesn't give you any privileged access. So so that was fine. And then it meant that we have working remote access working as well. So after you've got that, we use SSH for our recovery if we need to. We've got some more automated ways to control the devices as well, but this is like a last, nothing is working anymore, we need to recover our fleet or we're going bankrupt type vibe. So we retain SSH access by installing some authorized keys into the initramfs and copying over the SSH binary. So I just want to show, this is the same model that I mentioned in that one slide where there's essentially 3 steps. You add your binaries, you add your config files, and you add a service to start it up. It's the same thing for most things. So if you it all follows the simple model, which is again drag-out, making things very, very convenient, which is fantastic. Yeah. And then finally, we need to add monitoring. So we use Prometheus to monitor all our devices, and a node exporter is the main way to export metrics from your node. It's just a single Go binary, so it was quite simple to get this working in initRD as well. You just copy over the binary file into the initRD, add a systemd service. So you can actually export whatever you want there. It's very convenient to use text file exporters inside like bash scripts or whatever, because you just write to a file or whatever data you want to export as part of your metrics. So in our case, this is a really easy way to get an alert. For instance, if a device is stuck in recovery mode, we export this metric, and we've got some automated alerting to tell us that that's working, that's going wrong. And because we've got the VPN access, it means it's really easy to scrape these metrics as well. So yeah, that's it. So this brings all the 4 components together. So just quickly going over that again, you need a verified boot chain. So to get that working, you need your bootloader integration with the TPM. You need a TPM, and you need to get PCR prediction working. And finally, the TPM unlocking mechanism. So for that, you use Clevis or systemd-equipped setup or whatever you want to use. For recovery, we use Tang and Clevis again. There's other options as well. You can use your own key server if you want, but yeah, check out Tang, it's awesome. And then finally, for the monitoring and alerting, you can use whatever you use, but you need working networking, which you can achieve with either Network Manager or systemd networkd in your initRD, and some way to access the device. So however you usually do that. And yeah, that's it.
Questions?
Hi, I come more from this embedded world, so I'm a bit, I don't know much about this, so I hope you can enlighten me a bit about this TPM-based approach. Do you combine this then with the secure boot? I was wondering how in this scheme it's prevented that just known good values are being spoofed towards the TPM, so that in the end it will unlock your secrets even though the software that is currently running is not trusted.
Okay, yeah, so we don't combine this with secure boot because unfortunately we had to disable secure boot, but I think we've got a stronger guarantee by measuring all the system components. So instead of it just being, this is assigned to Ubuntu kernel, we know this is the exact Ubuntu kernel that we wanted to run. So you can't really spoof it because it's measured by the previous step in the boot chain. So the TPM will directly measure the FE firmware. The FE firmware will then measure the shim and grub executable. So that's before you start executing your own code. And then that will measure the next component of the bootload, which I believe will be the initRD. So the initRD is that's our main worry because that's where somebody can like stick some things in there. So that the entire initRD is hashed before it is, it won't be blocked, the execution won't be blocked, but once that's in the event log, you can no longer control what the event log hashes will be if you need to break the hash essentially in order to get it into a value that you want. So essentially, once the TPM is in a specific state, you can't really spoof a specific value into it because it's a append-only event log. So you can only add new hashes. So you need to figure out what hash you need to add to get to the value you want. So.
Yeah, thanks. So I was mostly wondering like how you establish a root of trust, but I guess you answered it by telling me that the TPM essentially controls your first boot stage.
Yeah, it doesn't necessarily control the first boot stage, but it does measure the component. So before it can get to unlocking the disk, the event log will already be populated with the values you expect. And if it's not the boot, the device won't unlock.
Thanks.
Cool.
Scott Constable with Intel Labs. Is your approach compatible with dynamic root of trust that could be established with a 1.2 or 2.0 TPM and either Intel TXT or AMD SVM?
To be honest, I'm not sure what those things are, but I'd love to. I'll check it out. But we just have I'm not sure, to be honest.
It's just a later stage of establishing a root of trust. Okay. It moves the earlier boot components up to the initramfs out of the TCP. So you start your secure boot by loading the kernel. So it's like the newer, although I guess it was new back in like 2008, 2009, but that's the more modern way of establishing a root of trust on at least x86 systems.
Okay, cool. I'll check it out. I'm not currently aware of how that works. But yeah, I'd love to chat with you afterwards and maybe, yeah.
Okay, thanks.
Hi, so you mentioned that there's a secret sharing scheme active, which means accessing the server alone won't give you the keys. Mm-hmm. So what happens in a scenario where somebody requests half of the key by asking the server and then steals a laptop? Is that person able to unlock because then they can just, you do not have verified boot anymore, or you do not need the TPM cooperation anymore because you can use recovery, have full access to the disk because you stole it, and previously you got the other half of the key. So how do you protect against that?
Yeah, so if you can read the LUX tokens, you essentially have an encrypted version of the key. So if you can then get access to the key recovery service, you can recover the key from that. But the idea is that you don't give access to the key recovery service just all the time. So that's why we wrap it with our own service that only gives you access under specific conditions. So when you know, okay, this was intentionally, this device was updated, whatever, and it broke, then we allow the access to that. But yes, so controlling access to the key recovery service is super important because otherwise, you just completely bypass the unlocking mechanism of the TPM. So it's meant as a last resort. Something went wrong. You need to get the device back online, but you can trust the device. That's only then that you actually open up the key recovery service.
Thank you.
Questions?
Thanks for your talk. I have a question, but first a comment about this append-only nature. You could reset the TPM, and if you and feed the values, feed fake values into the TPM, but it depends on your threat model if that's a problem with you. But you can't always like rely on this append only nature without extra steps because you can reset it.
Okay, cool. Thanks. I'll love to chat with you afterwards about that. Yeah.
Yeah, so my question is, you had the slide, they are non-numbered, this how do we determine what system state to trust? And you said you would predict these PCR values, but now you have multiple PCR values. If you are updating multiple components, can you just upload them into the TPM one by one and then commit them at once? Or what happens if you get like a power cut while you are updating the individual PCRs with the new values?
Yeah, so you so when you predict the PCR values, you predict all of them at once, and then with Clevis you provide your policy that you want to lock the secret with. So you say, okay, I want PCR 0 to be this and this and this and this. You give them all at once. So you update, I believe, all of them at once. I'm not sure what Clevis does under the hood when it talks to the TPM, but you don't set a specific PCR value like row by row. I believe you just give the entire policy and it locks it against that.
Okay, thank you.
Okay.
You mentioned that PCR 0 contains the firmware. Does that also mean that if I do a UEFI update, that my PCR 0 value will change? And if so, how do you handle those firmware updates in the field?
That is correct. That's one of the things that's a bit difficult. So the kernel updates and the initRD updates are relatively easy to handle. The firmware updates, though, you can plan for that and then roll it out as you need to. But yes, if you update your firmware, that's actually one of the things that will block the TPM from unlocking. But yeah, you can automate it. So if you set up, if you know beforehand what the hash is supposed to be, you can probably set it up to handle that appropriately.
So where do you get the new hashes then?
An easy way would be to just boot the system and look at that. So we've got this device, the underlying hardware is the same. So when we need to do that, we'll update the system and we need to plan the rollout and then know what the hashes is and then maybe lock an additional key against the new value and then roll out the firmware update and then it will unlock against that. But yeah, it's that's one thing. I'm not sure you can actually hook in. I'm not sure if you can hook into it, but we've got a script that handles the resealing of the TPM secret, and you can hook that into a bunch of parts of the system. So we've got a initramfs update hook. So whenever app updates the kernel, whatever, it will run that hook. I'm not sure if the firmware updating software, firmware update, I don't know if it has hooks that you can hook into, but if it does, it's probably quite easy to just hook it into there.
We had some more hands here. If somebody reminds me where it was.
Thank you. Very interesting talk. Just a comment or something I wonder. The update PCR step sounds to be maybe the weakest link in that. The confirming or verifying that you actually have the valid upstream kernel or something. Is that all manual, or do you rely on checksums, packet signing or something to make sure that you don't verify something that has been tampered with?
No, that's a valid point. So we essentially trust the system once it's online. So the threat model here is just once the system is online and it has actually unlocked the disk, we trust it. So there's other stuff we can obviously do to harden it once it's actually running. But we assume, okay, if you updated the kernel, app installed it or whatever, it already verified that the kernel is the correct kernel.
You just run predict on that and say that's good enough.
Yeah.
Thanks.
Other questions? Okay, let's thank the speaker.
Thank you.